I'll minimize this. Go up here. Okay, Hippocrates and the Quadrature of the Lune. Let's get to it. Okay. So Greece, okay, and in particular the Greeks, were kind of the dominant culture at the time that this was going on. Now we're talking about multiple centuries BC, okay? I think the time of Hippocrates would have been basically, you know, 3rd or 4th century BC. So it's a long time ago, you know what I'm saying? And the Greeks were particularly enthralled by symmetries and logical beauty as it pertained to geometry, okay? They sort of attached spiritual significance to it. Now exactly, you know, what their belief system was at the beginning versus what it turned out to be later on is something that I'll leave to Greek scholars to you know, talk about. But what I will say is there seemed to be an unusual obsession with things that were not physical. So kind of things that were abstract in the mind, intellectual, had great spiritual significance to the Greeks. And anything that was physical, they sort of discounted as bad. This is why later on in New Testament times, Paul had to work so hard to kind of remind the Corinthian believers, hey, the physical is actually good. And this is something that will be restored eventually in the new creation, okay? This is something that was constantly being warred against. And honestly, there's kind of been, because there's been such, you know, inculcation and obsession with the physical in our culture today, and like everything's physical now. It's like the opposite of what the Greeks were doing. Does that make sense? There's kind of been a move in Christendom back in the other direction. It's like the physical's bad, the spiritual is good, that sort of thing. So it's kind of back to the same Greek error as before. It's like, no, both of these things are good. And you know, look, there are things that we can enjoy in the body that are good things, that are good gifts from God. Okay, but the Greeks were particularly obsessed with the mental realm. Okay, particularly intriguing was the manner in which the simple and elementary could serve as a foundation for the complex and intricate. So they'd like to start with real simple ideas and see what could be built from those simple ideas. Okay, so the idea of proving things and logic all kind of found its roots in ancient Greece. Okay, a lot of like beauty that came out of the abstract was reflected even in their physical structures. They would kind of codify that even in their architecture. Okay, if you go and look at the Greek pantheon, the way that it was built was meant to reflect a lot of this beauty that they had discovered underlying things. Okay, so here's the rules of the game. Okay, all constructions. Okay, and this is just for this particular thing that the Greeks happen to be obsessed with. All constructions had to be done only with a compass and an unmarked straight edge. So a straight edge didn't have any markings on it, and the compass, I'm not talking about like a camping compass. Does that make sense? It's like a compass that you use where you have a metal point and a pencil and you draw a circle with it. Does that make sense? Those two items were seen as kind of like the most basic physical objects that, like, if I can't build something from this, then there's something mystical about it, right? So they were really obsessed with trying to construct things with only compass and straight edge, okay? As few physical requirements as possible, okay? So they're unsophisticated, but they were able to produce unbelievable figures with these things. And they would always try to say, okay, is it possible to bisect an angle just with compass, for instance, right? Is it possible to do this with a compass and straight edge? They were just wondering what sorts of things they could accomplish in the geometric realm with these objects, okay? Quadrature, okay? It's a fancy word. If you've ever heard of like the quadratic formula, that's talking about degree 2, second degree, right? Polynomials. Okay, it's what it deals with. And quadrature is the same. Degree 2, something's being squared. okay? And it's talking about area. And it's in particular, it's talking about the area of a square, okay? Because what's the formula for area of a square? Side times side, yes? So it's S squared, okay? So these seemingly unsophisticated tools can produce a rich set of constructions, from bisection of lines and angles, the drawing of parallels and perpendiculars, to the creation of really complicated polygons that had a lot of beautiful symmetries. But one thing that they were really obsessed with was trying to take complicated figures and figure out how to construct from that, just with compass and straight edge, from that a square of the same area. And if they were able to do that, they would call the starting figure squarable or quadrable. Okay? Of course, they had their own Greek terminology for that. So quadrature or squaring of a plane figure is the construction using only compass and straight edge of a square having area equal to that of the original figure. Okay? If this is the case, the figure is said to be quadrable or squarable. Okay? So look, obviously a square is quadrable, right? I mean, you don't have to do anything. You just stand there and look at it and you're like, ah, obviously I'm already done. The square is a square, yes? I don't even have to do anything, any swipes with my compass or my straight edge. Well, the very next object you would think that you would want to square would be a rectangle. It's not a square. Does that make sense? Hopefully, you've learned at some point that a rectangle is, right, or a square is a rectangle, but not every rectangle is a square, yes? Sort of a logical relationship. But let's say that we start with an arbitrary rectangle like this. How, or is it possible to square that rectangle? Is it possible to do that? So let's kind of read through this. It's actually possible, amazingly. Okay. So let ABCD be an arbitrary rectangle. Okay. We have that down here. And we want to construct a square that has area equal to that. So what did they do? They first extended the line AD, okay, out to the right with the straight edge. That's possible to do. Know what I'm saying? Okay. And then they used a compass to mark off segment DE with the same length CD. They could easily do that, right? By kind of placing the compass on the point D and swiping that thing out over here and kind of getting something. This right here is DE is the same length as CD. Yeah? Okay. And then the bisection would have been easy for them. I don't know if you've done this before, but you kind of extend a compass more than halfway across a line segment, and you kind of mark off an arc, and then you keep the thing open, the same length, go the other side and do it on the other side. And where those two arcs cross, you kind of can draw a straight line down and get a perpendicular bisector, actually. It's not just bisected, that segment, but actually something that would be at a 90-degree angle to it, okay? So let's bisect AE at that point O, okay? And then what you do is you basically make a circle or a semicircle that goes from A over to E, okay? So make that little semicircle right there, okay? So of course AO is equal to EO because after all you know that's the radius of the circle. Okay. At D you construct a line DH which is perpendicular to right. So perpendicular to AE. Okay. And H is just the point where that thing goes up and hits that. And by the way, you could even do that just with a straight edge. You just put the straight edge right on CD and go straight up until you actually hit the circle right there. These are all things that they would have been able to handle fairly easily, okay? And then you construct the desired square, DF, so DH is one of the sides right there that we get, and then you can actually just take that side and copy it to all four of those sides. The Greeks would have easily been able to do that, and there's your square right there, DFGH, okay? Now the question is, Why is that a square that has the same area as the original rectangle? Yeah? And who on earth would come up with this construction? Who knows? But they did it, okay? Which is sort of amazing. So let's see why this thing happens to have the same area, okay? Why does that square that we just constructed, DFGH, have the same area as the rectangle ABCD? Well, label the hypotenuse. Okay, see that little right triangle right there, OHD? There's a little right triangle right there. OH is a radius of the circle that we drew, yes? Okay, so you label that hypotenuse A. You label the length from O to D, B, and from D to H, you label that C, okay? By the Pythagorean theorem, you know that A squared is equal to B squared plus C squared. And the Greeks were absolutely obsessed with that fact, okay? Of course, Pythagoras himself was part of, one of the quintessential Greek mathematicians and thinkers. They would have been acutely aware of that fact. So, I mean, just rearranging that, A squared minus B squared is equal to C squared. Okay, a couple of observations. Notice that DE, see DE right there, kind of dangling off the end? That is the same thing as A. Do you see, like, look, go from O to E. Do you guys see that from O to E is the same as A, the length A? Yes, it's a radius of the circle, okay? So DE is equal to, it's CD also, by the way, because DE and CD were constructed to be the same. DE is A, that whole thing, the whole radius, minus B, yes? It's the whole radius minus B. That would give you DE, which is the same as CD. And AD, which is the top length of that rectangle, what's that? A plus B, yeah? So A minus B is basically the same as CD, and A plus B is the same as AD, but that's just width and height. Do you understand what I'm saying here? That's the width and height of the original rectangle. So the area of the rectangle is AD times CD, which is A plus B times A minus B, which is A squared minus B squared, which is C squared, which is exactly the area of that square dangling off to the upper right there, yes? So that is the argument for why that construction delivered a squaring of that rectangle. Yeah, it's pretty cool. Yes?
How did they find, like,
Well, that was just constructed, right, because they extended this out some arbitrary length. F was constructed once they had this side, right, the DH. Once they had DH, they could take one side of a square and then they would, once they had one side, it was over. They could just construct the entire square easily, They have that length, they could copy it and put it at 90-degree angles at each one of those things. Okay? That's an interesting construction to think through. You could probably come up with it on your own, actually. It's not that bad. Yes, sir.
I know I'm probably not saying it right now, but why is A minus B the same as CD?
Why is A minus B the same thing? Okay, CD is the same as DE. Yes? CD is the same as DE. DE, how do I get DE? Well, DE is the entire length from O to E. What's O to E? That's the radius, A. And then I have to get rid of that little length right there, B. So that's why it's A minus B. Yeah? Other questions? It's pretty cool. All right. Next. We know how to do it. Remember, what's our goal? We want to figure out what sorts of things are squareable. You know what I'm saying? What sorts of things are squareable? Okay. So next, what about a triangle? Okay. Well, it turns out a triangle isn't really that hard to deal with either. So somebody hands us an arbitrary triangle, ABC. Okay. We want to find a square, construct a square from this triangle that has the same area. That's the goal, yes? With only compass and straight edge, want to construct a square that has the same area as the triangle. But now we know how to turn any rectangle into a square, yes? So what the Greeks said is, it's enough for me to take the triangle and actually find a rectangle with the same area. Does that make sense? Because then I know I can take the rectangle and turn it into a square. That was kind of the sequence of thoughts that they had. Okay? So the first thing they did is they dropped a perpendicular from C down to the base. That's just totally trivial for the Greeks. Okay, that's another one that you can almost come up with on your own. They were able, if you gave a point in any line, they could actually draw a perpendicular through that point down to the other line, okay, with just a compass and straight edge. You could actually probably come up with that on your own, okay? We know that the area of the triangle is obviously 1/2 times AB times CH. CH is the height of that triangle, yes? Okay, 1/2 base times height. The other thing the Greeks could do is trivially, they would be able to bisect that segment CH, right? They would be able to do that. That's a bisection of a line segment is easy to do, okay? So they bisect it at that point M, and then all they have to do is just basically draw a parallel segment right here, kind of extend these sides up. That would have been fairly simple for them to do. What's the area of that rectangle? Well, the area of that rectangle is AB times 1/2 the height, which is exactly the same as the area of the triangle, yes? And then they say to themselves, we're done, because I know that from this rectangle I can now construct a corresponding square, yeah? Any questions on that? Yeah.
How do you find point 1?
That's just, there's an easy construction to find the midpoint of a segment. Right, you just basically, what you do is like at C, you would put the point of the compass, you would make sure you go out at least halfway, you kind of strike out an arc, and then you go the other side, strike out an arc, and then what you do is kind of connect the places where those two arcs meet each other, and that's going to give you the midpoint. It's a pretty standard construction. Are we good? We can do a rectangle, we can do a triangle. Hey, let's try to do something more complicated. I don't know, like a pentagon or something. Or how about any polygon? A polygon is, you know, a sort of many-sided shape. Okay, so let's talk about the quadrature of a polygon. Can we construct a square that has the same area of a given polygon? Okay. Well, here's how they thought about it. They said, well, any polygon, I can kind of break it up into triangles. Does that make sense? So they said we can break it up into triangles. I know how to square all those triangles, but the problem here is I might have like, I don't just want like a bunch of squares. I want one square. Does that make sense? It's one thing to like take one of those triangles and construct one square equal to the area of that one triangle. It's another thing to try to take a bunch of triangles and create one square that's the area of all of them combined. Does that make sense? So here's what they did. This is pretty nice, okay? They went like this. They said, we can construct squares with sides. So for instance, this one right here, A1, that area, they know they can square that, right? They know they can construct a square of that area. And let's say that the side length of that square is little a1, okay? Same thing with capital A2. That area can be squared with a square of side length A2. And then A3, that could be squared with a side length A3. Make sense? We know that we can do that individually. So far, so good. But that's not what we want. We don't want a whole bunch of squares. What do we want in the end? One. We want one square. And this is where, this is just sheer genius. So watch what they do. They said, okay, I have all of these lengths, little a1, little a2, little a3, that comes from those individual squares, yes? Now watch what they do. They said, okay, I am going to take the first two of those, a1 and a2, and I'm going to make a little, like that length and that little a1 and little a2, I'm going to make a kind of one segment of one length and then the segment of A2, and I'm going to make them at a right angle to one another. They could easily do that. There's a construction that they would do. And then I'm going to draw the diagonal on that right triangle. Yes? Now, what's true about that diagonal, d1 squared? What's the Pythagorean theorem say that's going to be equal to? d1 squared will be a1 squared plus a2 squared. What? You see it? So what they've done is they've basically taken two squares, and they would be able to construct a square of side lengths d1 over here. Taken those two squares and they've made it into one square, because a1 squared plus a2 squared equals d1 squared. Does that make sense? Yeah? And they just extend that idea. They say, well, here's this diagonal. I'm going to slap on this other length, a3 right here. These are at right angle to one another. It's a right angle right there. Yes? And then so what they did with that is they said, okay, now I'm going to look at that hypotenuse. That hypotenuse is, what's the relationship? d2 squared is equal to d1 squared plus a3 squared. But what's d1 squared again? n1 squared plus a2 squared. So d2 squared is equal to a1 squared plus a2 squared plus a3 squared. It's the sum of those squares, yes? And that's the total area right there, yeah? So they were able to kind of take these little right triangles and build them off of diagonals, and in that way eventually produce a square that has the same combined area of all those triangles, yes? Brilliant. Any questions on that? Questions? And you see how this would extend, right? If they had a fourth one, you would just put that length out here, draw the diagonal, etc. On and on and on it goes. Yeah? And kind of corkscrew around or something. All right. Obviously, this procedure can be adapted to the situation in which the polygon is divided into any number of triangles. Yes? It's amazing. So no matter how complicated the polygon is, they can construct a square. They can construct a square that has the same area of the original polygon. Yeah? So they said to themselves, okay, oh, and by the way, they actually had a technique, and you can read about this in the chapter. They had a technique whereby you could add areas together like we just did. So squareable areas could be added together by doing the little right triangle construction and drawing one big square that's the combined areas. But they also had a way to deal with differences of areas. Like if I wanted to take one area away from another area, they could actually deal with that, okay? It's interesting. So they thought, well, good grief. What's stopping us now? Why can't we just do shapes that actually have curvy, like all the polygons have straight line, they're called rectilinear shapes, yes? But what about things that have curvy lines in them, yes? They thought to themselves, well, it seems like we should be able to do that, since after all, I could basically approximate any curvy line shape with a polygon. Does that make sense? So like, there's got to be a way to pull this off. Okay, so they were interested in going from the rectilinear situation, like the polygon straight line segment situation, to curvilinear figures. Okay? So, I mean, the book mentions, there's this quote in the book says, initially this must have seemed unlikely, for there is no obvious means to straighten out curved lines with compass and straight edge. I don't know what the Greeks were thinking, but if I were back in those days, I actually would have thought the opposite. I would have thought, well, good grief, no matter how complicated the polygon is, I know how to square it, yes? And so it seems like there ought to be a way through approximation or something to actually pull it off, right? So it's not that surprising to me that they were obsessed with trying to deal with curvilinear figures. Okay, here are three famous problems that the Greeks were obsessed with. The first is the so-called trisection of an angle. Angle bisection is easy. Angle trisection turns out is impossible for arbitrary. I mean, there is a way to trisect certain angles, but not every angle, okay? So that's interesting. Duplication of the cube. What that means is, okay, well, it says it right here. Find the side of a cube of which the volume is twice that of a given cube. Okay? This is called the Delian problem. So in other words, somebody gives me a cube and I want to construct another cube where the volume is double that. And by the way, it's no good just doubling all the sides. That's going to have 8 times the volume. You understand what I'm saying? So somebody hands me a cube. From that, construct a second cube that has double the volume. So doubling the cube. And the other problem that they were obsessed with, because they were trying to move into the realm of curvilinear figures versus rectilinear, what's the simplest of curvilinear figures that you can think of? A circle. And they're like, if we can't handle a circle, what can we handle? Yeah? So the first place they go is the circle. The quadrature of the circle, that is, find the square of an area equal to that of a given circle. Okay, so those were the big 3. Trisection of an angle, duplication of the cube, and quadrature of the circle, all done with, compass and straight edge. Does that make sense? Yeah? So, but we're going to hone in on this third one, quadrature of the circle, since we're talking about quadrature. Oops, I have a typo there. That's not how you spell Aristotle. But let's talk about Hippocrates of Chios. And again, we're talking, actually, he was in the 5th century BC, so way back, know what I'm saying? Aristotle wrote of him that he seemed, in other respects, to have been stupid and lacking in sense. It's sort of a typical mathematician back in ancient times, 2,500 years ago. Okay, legend has it that Hippocrates earned his reputation after being defrauded of his fortune by pirates, who apparently took him for an easy mark, right? So sort of lacked common sense, but was just a brilliant geometric and mathematical genius. So needing to make financial recovery, traveled to Athens and began teaching. Okay, so 2 important contributions. Apparently, he wrote a first composition of the Elements. You've probably heard of that before. Euclid is the one that's typically credited with having written the Elements. But apparently Hippocrates before him had actually written kind of an early copy of that. And his Quadrature of the Lune is something he's very famous for. So we're about to see that. The reason that it was so famous is because it was really it was the first significant step toward squaring the circle at a very specific kind of curvilinear figure that he was able to square. And no one else was able to pull that off before. Okay? So he is credited, since nothing remains, right? So this is sort of questionable, since nothing remains today. I mean, it's hard to separate fact or myth from fact in some of these cases. But he's credited with writing the first Elements, first exposition developing the theorems of geometry precisely and logically from a few given basic axioms, things that you were allowed to assume. Whatever merits his book had were to be eclipsed by the great Euclid when he actually put together the Elements and organized basically all of Greek thought as it pertained to geometry at that time. It was basically, Euclid just organized most of what was known. That's kind of his primary contribution. But he also had some new stuff in there as well. Right, still there's reason to believe that Euclid borrowed from Hippocrates' treatise that he had written. So in his attempt to organize some of this stuff. All right, let's talk about the Lune. Okay. This had to have been a shock when he squared this thing. Okay, you're going to see what it is. You're going to see that it looks somewhat like a circle or circular in nature. The first time that this gets talked about, though, is Eudemus, which is almost 100 years, or actually a little over 100 years later, okay, 335 BC. But that's even murky because you don't really have that account either. It's actually Simplicius' account from 530 AD. It's almost like 1,000 years after all this happened, right? But Eudemus is known as kind of a reliable source. So it's almost certain that this is due to Hippocrates. But some of the questions are, okay, well, is this precisely how Hippocrates did it? Or is this like a simplification of it, or what? That's where we're kind of unclear. It seems for sure that Hippocrates did this. This is a lune. It's that dark gray shape right there. You see why it would be called a lune? It looks kind of like a crescent moon of some kind, yes? It's basically a circle from which part of another circle has been removed, yeah? And you know, the Greeks were primarily interested in first dealing with the semicircle, like a half circle, because if you know, there's some nice properties that a half circle has, namely like there's a diameter right there you could work with. Okay, so let's deal with this thing. This is actually the lune that he found that he actually worked with. Okay. Hippocrates didn't square all lunes. He did not do that, but he did a careful squaring of a particular kind of lune, namely the one that was on the previous slide, and that we'll have that here in just a minute as well. Again, up on the screen. 3 basic facts that he needed: the Pythagorean theorem. Yep. Okay, we're good to go with that. That an angle inscribed in a semicircle is right. Okay, so this comes from the fact here. I'm going to write on here, and we'll see if you can see this. So if I take a circle, okay, you guys see that? Oops, that's not good. I'm going to put it where it actually is alive and well. Okay, so here's a circle like that. Yeah. If I actually inscribe any angle in this circle like that, and this is the center of that circle, how does this angle, do any of you know? So like this angle, if I call this angle alpha, for instance, the original angle alpha, how does that relate to this angle right here? Do you know? It's twice. Okay, that's something that that I would challenge you to go do. It's actually a fun exercise. Okay, it's not that hard to actually figure out why that happens to be the case. But that angle right there is 2 times alpha. Okay, so it's twice that thing. Yeah. Therefore, if I take a circle, okay, and here's a diameter of that circle, and I, you know, and I inscribe, so like this, so this angle that I'm drawing right here is right on that diameter. What is this angle? Okay, so this angle right here, alpha, what is it? Well, this angle right here, that's equal to 2 times alpha, but what is that angle? That's 180 degrees, do you understand? So what's alpha have to equal? That's 90 degrees. So that's why an angle inscribed in a semicircle, that means it sort of is on the diameter, that thing has to be right. Yes? So this is just a particular application of that thing we just talked about. Okay? And the third thing he needed, which wasn't really that big of a deal either, was that the area of 2 circles or semicircles are to each other as the squares of their diameters. Okay, that's pretty easy. Because, okay, like if I take like A1 is equal to pi R1 squared, yes? And A2 is equal to pi R2 squared, okay? Then if I take A1 over A2, okay, that's what he's talking about. I mean, Greeks kind of talk in a weird way. R to each other, that just means like when you take the ratio of the two, what are you going to get? R1 squared over R2 squared. Okay, and if you just multiply and divide by 4, okay, if you multiply this by 4 over 4, then you could take the 2 times the radius or squared, and then 2 times radius squared. You guys realize that that's going to be like D1 squared over D2 squared. Right? It's going to be the first diameter squared over the second diameter squared. So that's what I mean by the area of two circles are two semicircles are to each other as the squares of their diameter. Does that make sense? They said semicircles. I was talking about the entire circle, but you know what I mean. Okay, it's not that different. Okay, so those were the three facts that he kind of needed to pull off what he was going to do. So let's look at that. Well, the last proposition that the area of the squares are to the squares of the diameters, there's some speculation as to whether he actually had a proof of that. As we'll see later on, it really seems like Archimedes was the first person to pull this off, and that would have been, a couple hundred years later. So there's speculation as to whether he would have actually known that or just suspected that it was true. Does that make sense? But it is true, and it's going to form part of his argument. Okay, the thing about the areas of squares being equal to the ratio of, like the ratio of areas of squares being equal to the ratio of squares of diameters, that actually does appear in Euclid's Elements later on. Okay, let's look at this thing. Here's what we do. Okay, so here's how the argument goes. Start with a semicircle. Okay, so I have this semicircle right here. It's pretty easy to construct a semicircle. Fine. Okay. Construct OC, which is perpendicular to AB, and it's like the perpendicular bisector. So that OC right there, that would be trivial for the Greeks to do. And notice that this is going to split the semicircle exactly in half. Yes? Okay. And then what you do is you bisect this segment AC right here at D, and then you kind of swipe out this other semicircle. Yeah? Okay. And eventually you end up with this Lune AECF. Yes? So this semicircle right here basically sits on half of this original semicircle. The upper semicircle sits on exactly half of the other one. That's the Lune construction that, Hippocrates is dealing with. But what we want to show is that Lune, AECF, is quadrable, squarable, that we can construct a square that has the same area as that thing. The way we're going to do that is we're going to show that the Lune has the same area as that shaded triangle right there. And what do we know about triangles? They're quadrable, and therefore we would be done. So if we can just show that the Lune right there has the same area as that right triangle, we're done. Yeah? Okay. All right. So the first thing you had to do is exactly what I just said, establish that the Lune in question had precisely the same area as the shaded triangle AOC. Okay. And then all you had to do was just apply the fact that triangles are quadrable. That's it. So here we go. Note that ACB is a right triangle. Why? Why is ACB a right triangle? Because it's an angle inscribed in a semicircle, yes? So the angle ACB is a right angle. Okay, and triangles AOC and BOC are congruent. Why? Well, this is a perpendicular bisector. All of the sides are just radii, yes? You have AO, OB, and CO. So you could use like side, angle, side if you wanted to, yes? This would have been something that would have just been child's play for someone like Hippocrates, right? Okay, so you have those two triangles right there that are right and congruent. That means that AC is the same as BC, yes? Since those two triangles are congruent. Okay? So you can apply the Pythagorean theorem. So you know that AB squared, that's the hypotenuse of this thing right here, is equal to AC squared plus BC squared, because again, I have this right triangle that's kind of sitting on its hypotenuse, but BC is the same as AC. So AB squared is equal to 2 AC squared, yes? Okay? So what about the semicircle AEC? Okay, so let's look at the semicircle AEC. So that means that's not the Lune, but it's that semicircle sitting out there, AEC. Yes? Okay? That has half the area of the semicircle ACB. Okay, that's the claim, that it has half the area of the semicircle ACB. Well, okay, why? Well, because the area of semicircle AEC, if I divide that by the area of semicircle ACB, well, that's got to be equal to, he's using the fact that that's going to be equal to the ratio of the diameters, the squares of the diameters, yes? So this ratio is the same as the ratio of the squares of the diameters. That's what he's saying here. Okay, so AC squared, that is the small semicircle, and AB squared, that is the bigger semicircle, yes? So the ratio of the areas is the same as the ratio of the squares on the diameters. Yeah? Well, what's AB squared? 2AC squared, yes? So what's going to happen to the AC squares? They cancel, and you end up with a half. So what this says is that the area of this small semicircle is half the area of the big semicircle. Yeah? That's important. Let me explain why quickly. It's because the area of AEC is therefore the same as this like quarter circle, AFCO, yes? And now you could probably see where this is going to go. Now all you have to do is remove the part that they have in common. Does that make sense? And he's done. He's basically showed that that triangle is going to have the same area as that Lune. But that's what's going to be on the next slide here. Okay, so let's look at that. Semicircle AEC has half the area of semicircle ACB. Quadrant AFCO has half the area of semicircle ACB. So, duh. Area of semicircle AEC is the same as the area of quadrant AFCO, that quarter circle. Yeah? So subtracting the area of the shaded region AFCD, what do we get? You're just going to have area of semicircle AEC minus that area, area of that overlapping region. It's equal to the area of the quadrant AFCO minus the area of that region. But that, look at that. If I take AEC and I subtract out that region, I get the Lune. Yes? Therefore, the area of the Lune is the same as the area of triangle ACO. And what do we know is true about that triangle? Quadruple. And so he's squared the Lune. At least that one that he constructed specially right there. Okay? Here's a little epilogue. Just a couple-minute epilogue here. So they immediately thought, okay, it seems like we're going to be able to do a lot of stuff here now. Yes? I mean, this technique that Hippocrates had seems like it was a move in the direction of squaring the circle. And they put a lot of time into kind of pursuing things like what Hippocrates had done. In fact, here's another, sort of construction, okay? Or how you might actually try to square the circle. You kind of construct a sequence of lunes. You kind of construct a sequence of lunes that are built on like a little hexagon that you inscribe in the original circle, okay? You can show that those lunes right there actually equal the area of the circle on the inside. That's something that you can actually prove, okay? And then what the Greeks did is they said, oh, since we can square those lunes, we're done. No, these lunes are not squareable because these aren't the same type. Look, I mean, remember before this thing was built on like a quarter of a circle, not like some weird like 60-degree angle or something like that. Turns out that those things are not squareable. Okay, so an attempt like this does not work. It turns out that there's very few lunes that are actually squareable. In fact, I think, actually I'm going to skip this part. I just kind of explained it. The glaring hole in the argument is the lunes that Hippocrates squared were not constructed along the sides of hexagons, but on the side of a square. Yeah. And the problem of squaring the circle was unsolved for over 2,000 years, actually, more than 2,500, probably 2,400 years after Hippocrates. In 1882, Ferdinand Lindemann proved that you could not square the circle, but he had to do it with some pretty sophisticated mathematics. Okay? In order to prove it, he had to show that pi was transcendental. What that means is that it's not the solution of any polynomial equation with integer coefficients. It's pretty hard to do that. Turns out that there's only 5 types of lunes that are quadruple. 3 were actually discovered by Hippocrates, so he did this one in addition to 2 others. And actually 2 other ones were found by Leonhard Euler in the 18th century later on. We'll talk about Euler later on though. And in the 20th century, Chabataro and Dorodnow actually showed that these are the only quadruple lunes. These 5 are the only ones that are quadruple. That's sort of interesting. Okay, that's it. Okay, that's chapter 1. It just kind of gives you a flavor of the sort of thing that's done in there. Typically, you focus on a period of time, a particular mathematician, and a great theorem that was done there. Okay. One reason I wanted to do this is I wanted to kind of get your juices flowing in terms of thinking about how proofs go, okay? How the logical flow of a proof goes, but we'll sort of formalize this together in this class eventually, okay? I'm gonna post this presentation in Moodle. I'll put it under a module that's exclusively devoted to just classroom slides or whatever, so that you can have access to this. But on Monday, I'm expecting you to write a little 500-word response on this. And you can't just write, wow, awesome, amazing 500 times, right? I want like a real sort of digestive response of this thing. But you can go and kind of read through the chapter. There's some nice little tidbits in there in addition to this. But that is all for now. Okay? It'll in Canvas. You'll just upload it into Canvas. Yeah, I'll make that assignment pretty soon. All right. You guys doing all right? All right. Thank you guys. See ya.